DC circuits. Introduction to capacitors. Capacitors are storage elements. They store energy. With the introduction of capacitors, we can analyze more important and practical circuits. Capacitors are passive elements. Figure 1 is a typical capacitor. This is a parallel plate capacitor. It consists of two conducting plates separated by an insulator or dielectric material. And so looking at figure 1, you have this conducting plate with surface area A, and this is another conducting plate with surface area A, and in the middle is a dielectric material with permittivity. And this is the distance between this plate and that plate. And then this is the lead. This is the positive lead and the negative lead. And when we go to fig 2, it's basically this capacitor in a circuit. And we apply a potential difference to the capacitor, and then the current is going to flow clockwise. So what is going to happen is that we're going to have positive charges on this black plate and negative charges on this green plate, and the charge per plate is proportional to the potential difference applied. Now, potential difference is always across an element, and current is always through the element. So when we go down from here, Q equals CV. Q is the charge per plate, C is the capacitance of the capacitor, and V is the voltage applied across the capacitor. So from equation 1, we have C equals Q divided by V. So the capacitance is equal to the charge per plate divided by the voltage. So we do some dimensional analysis here. Capacitance is measured in farads, and 1 farad is 1 capacitance divided by volts. All right. Capacitance per volt, basically. And equation 2 says that the capacitance is equal to some constant, this guy, times A, which is the surface area per plate, divided by the distance between the two plates. So that is equation 2. So the value of this capacitance depends on the physical properties of the capacitor. And equation 1 is we got equation 1 from up here, that the charge per plate is proportional to the potential difference applied. And let's go up here. So from equation 2, it means that if we increase the surface area, we increase the capacitance. Also, if we decrease this distance, we increase the capacitance. All right. And this is the circuit symbol. Figure 3 is a circuit symbol for a capacitor. This one on the left is a fixed type capacitor. And this one here on the right is a variable type capacitor. So we can describe a capacitor based on fixed type or variable type. So that is Fig 3, circuit symbols for capacitors. And the power absorbed by the capacitor is equal to the voltage times the current. And if the power is positive, it implies that the capacitor is being charged. And if the power is negative, it implies that the capacitor is discharging. All right. And the passive sign convention, this means that the current must enter through the positive terminal of a circuit element, and the power should be positive. So that is basically the passive sign convention. The passive sign convention is satisfied when the current enters the positive terminal of an element. All right. And some uses of capacitors. Number one, they are used in radio receivers to tune to various stations. And number two, they are used to block DC signals, pass AC signals, shift phase, store energy, start motors, and suppress noise. All right. And let's look at some fixed capacitor types. So this capacitor is being described by the type of dielectric material. So when you look at here, it said element, material, ceramic. So it means that this is a ceramic. All right. So we can describe the capacitor by fixed type or variable type. And we can also describe it by the type of the dielectric material or insulation, between the plates. And then when we go to this one is also fixed type capacitor, and the dielectric material is polyester, right? And this one, another fixed type capacitor, and here the dielectric material is electrolytic, right? All right, so Fig 4, those are fixed type capacitors. And Fig 5 is a variable capacitor, right? And you vary the capacitance by turning the shaft, all right? From equation 1, we saw that Q is equal to CV. Let's take the derivative of both sides of this equation. So you have d dt of Q on the left-hand side. On the right-hand side, d dt of CV. And so here you have dq dt. This c comes down here. And you have dv dt here, right? But dq dt is I. I is the current. All right, so I is equal to dq dt. And let's call this equation 3. All right. This implies that the current, right, which is this guy, is equal to the capacitance times the derivative of the voltage. All right, so that is equation 4. And this is the current voltage relationship for a capacitor, assuming the passive sign convention. All right. So that is equation 4. And this figure 6 is the current voltage relationship of a capacitor. So on the y-axis you have the current, and the y-axis you have the VDT, and the slope is equal to the capacitance. How do we obtain the voltage current relation of the capacitor? From equation 4, the current is equal to the capacitance times the derivative of the voltage, right? So I equals C times dV dt. This is just this equation, but I've written it with, I just wanted to point out that this current is a function of time, and this voltage is a function of time. This is still equation 4, right? Okay, this is the same equation. So this is I of t equals C times dV dt, right? It's the same equation that I've written down here. All right. And let's take the integral of both sides of equation 4. So we take the integral of I of t with respect to t from minus infinity to t. And on the right hand side, we have integral, we have the integral from minus infinity to t of this function with respect to t. Now, this dt and this dt cancel out. This I is this I. There is an integral from minus infinity to t with respect to t, right? This dv dt is this dv dt, right? This c is this c. We're going from here to here. We're integrating with respect to t. And we here, from this equation, we get this equation, all right? So from here, we get here, all right? From here, we get to this place, all right? And I also want to point out that I don't know if I did point this out. You cannot integrate with respect to t and have a t as a limit on the integral. You're going to get an error. It's going to say something like error, dependent limit. Like if you try to do this integration with, let's say, your TI-89 calculator, you can't do this, all right? So what we do is we integrate with respect to tau, all right? And then we take the limit from minus infinity to t, all right? And then from here, we get here, all right? So this is basically the voltage is a function of time. We evaluate it at minus infinity and t, all right? And this is basically, I've just brought this down here. And so from here, we get to this, we get here. So this is v of t minus v at minus infinity equals this, right? We just brought this down here. So this implies that v of t equals 1 over c the integral of t with respect to tau from minus infinity to t, and we note that here this one is 0, all right, because at some time, at minus infinity, the capacitor was not charged, it was uncharged. So for that reason, this guy is 0. Or instead of integrating from minus infinity to t, we can integrate from t0 to t, all right? So we do the same thing on the right-hand side, right? t0 to t. And if we do the integration this way, from here, we get here, all right? And then we get here. And then we get here. And then we get here, all right? And so from here, we take this to the right, and we arrive at equation 6, all right? And this guy is equal to the charge per plate at T0 divided by the capacitance, all right? And here I redraw fig 2, okay? And the power is the voltage times the current. So this V is this V, this I is this C divided T. All right, so this implies that the power absorbed by the capacitor is equal to CV times divided T. All right, and this W is energy. Energy is simply the integral of power. So this is the integral of the power, right, with respect to tau, right, from minus infinity to t, all right? And this power, right, is this C V divided t. This dt here is this one, right? We are integrating with respect to t. Okay, so this is actually the tau, right? Because we can't have the t here and still have t on the limit of integration. So this is the tau, and then we make this also the tau. So this cancels this. So from here, we get here, all right? So this c is this c, this is this integral, right? This is v of t, this is the v, all right? So when we integrate this is what we get, all right? And from here, we get this. And this V at minus infinity is 0 because the capacitor was uncharged at t equals minus infinity. Hence, the energy is equal to, this is some constant, which is 0.5, right, half, some constant, times the capacitance times the voltage squared, or simply W equals half CV squared, and this is equation 9, all right? Recall that the charge per plate is equal to the capacitance times the voltage, right? This is equation 1 that we derived earlier, right? So I just, I just wrote it down here for convenience. So So from here, the energy is equal to half times C times V squared. But V is equal to Q divided by C. All right. So from here, we have half times C times Q times 1 over C times 1 over C. And this C cancels this C. This implies that the energy is equal to Q squared divided by 2C. And this is equation 10. Note, equation 9 or equation 10 represent the energy stored in the electric field that exists between the plates of the capacitor. All right. And here, these are very key properties of a capacitor. Number one, a capacitor is an open circuit to DC. All right. A capacitor is an open circuit to DC. However, if a battery is connected across a capacitor, the capacitor charges. And let's prove it. Let's prove it. Not prove. So look at equation 4, right? Current equals C times dV dt. Now, what happens if V of t is constant? Your current is 0. This implies that you have an open circuit, right? This implies that there's an open circuit there. All right. Number 2, the voltage on a capacitor cannot change instantaneously or abruptly. It cannot change. However, the current through a capacitor can change instantaneously. All right. So we look at figure 7, voltage across a capacitor. So this is allowed. It can do something like this and that. It comes down a little bit, right? But you can't do this. You cannot just go from here and you jump, and then you jump again. An abrupt change is not possible. So this is not allowed. All right. And then let's look at some examples. Example number 1. So what is the voltage across a 4.5 microfarad capacitor if the charge on one plate is 0.12 millicoulombs? How much energy is stored in the capacitor? All right, so Q equals CV, right? This implies that V equals Q divided by C. All right, so this is equal to, this is Q, right? This is Q divided by C, and C is 4.5 microfarad. So this implies that, we just plug in the numbers, right? And we get 26.67 volts. How much energy is stored? The energy is this equation. So this half, this is C, and this is V, right? And then we just, this half, this is 4.5 micro, this is 26.67. This gives you that, all right? And this is 1, right? 10 to the power 3 times 10 to the power negative 3 is just 1. And we can multiply this and that to get 1.6. And this is just milli, right? So this 1.6 millijoules. All right. let's look at example 2. All right. So if a 10 microfarad capacitor is connected to a voltage source with voltage, this is a voltage, find the current through the capacitor, right? So we just want to find I, all right? Recall, I is equal to C times dV/dt. This implies that I equals this is C, this is d dt of V, and this is V. So this is 10, this is micro. D dt of this gives you this cosine function, and we get 1.5 times this cosine function, right? And this is current, so it's in amps, right? Okay, and there's another example, example 3. The current through a 100 microfarad capacitor is this, right? Calculate the voltage across it at t equals 1 milliseconds and t equals 5 milliseconds. Take V at 0 to be 0. So recall that V of t is this, all right? And this implies that V at t equals 1 milliseconds is equal to this, all right? And once we take the integral, we get this, and then we simplify it some, and then we get 93.14 millivolts. And then V at t equals 5 milliseconds. This is equal to this. We take the integral, we simplify it, and we get that. All right. And this is another example, example 4. An initially uncharged 1 millifarad capacitor has the current shown in the figure above. Calculate the voltage across it at t equals 2 milliseconds and t equals 5 milliseconds. So this is the current, this is time, this is the current, right? So the current is 0. Then at 2 milliseconds is 100 milliamps. Then from 2 milliseconds to 6 milliseconds, it stays constant. So here I made this 0.1, I made this 0.2, this 0.3. All right. So let's find the equation of a straight line between P1 and P2. Recall that the change in Y divided by the change in X is equal to this. Hence, this is the change in the current divided by the change in time, and this is equal to this, all right? So this implies that, I of t is equal to 50t, all right? T going from 0 milliseconds to 2 milliseconds. Let's find the equation of a straight line between P2 and P3. So we do the same thing for P2 and P3, right? There's a change in current, change in time is equal to this. And from here we get here, all right? Because this is 0. This one is 0. So that is just 0. And then we bring this one here, and then we solve for I of t, and I of t is 0.1 amps, t going from 2 milliseconds to 6 milliseconds. Hence, this I of t is equal to 50t when t is between 0 and 2, and this is 0.1 when t is between 2 and 6, and is 0 otherwise, right? The voltage at t equals 2 milliseconds is equal to this, all right, plus 0, all right, because the capacitor is initially on charge. So once we simplify this, we get 100 millivolts, all right, and the voltage at t equals 5 milliseconds is equal to the 100 millivolts plus this. So this 100 is, we bring it down here, we simplify this, all right, and we get 300 millivolts. Okay, so we add this to that, we get 400. All right, let's look at the final example. Example 5. Under DC conditions, find the energy stored in the capacitors in the figure below. So this is the circuit. Now remember, a capacitor is an open circuit under DC conditions. From equation 4, we have this, right? So what happens if V is constant, right? The current is 0, right? So just remember, this capacitor is an open circuit at DC, all right? So we just, here, you see we open the circuit here, all right? And here, we open the circuit here. And from here, we use nodal analysis to find the node voltages V1, V2, and V3. And so doing nodal analysis, this is ground, this V1 is 50, okay? And at node 2, the current that is coming in here leaves here, right? So this current coming in is V1 minus V2 divided by 1,000 is equal to the current that is leaving is V2 minus V3 divided by 3,000, right? So this is equation 2. And at node 3, the current that is coming in is this one coming in, and it leaves that way. So what is coming in is V2 minus V3 divided by 3,000 equals V3 minus 0, or simply V3 divided by 6,000, all right? And also remember, current always flows from a higher potential to a lower potential in a resistor, right? So the current, if there's a higher potential, there's a lower potential, current is going to flow this way, right? And since we have an open circuit here, the current is going to go this way and that way back to ground, right? So solving these equations, set of simultaneous equations, 3 equations, 3 unknowns. You have V1 is 50, V2 is 45, V3 is 30, all right? So from Ohm's law, we have V equals IR. This implies that I is V divided by R, and if you just, put 30 here, 30 volts here, and this R, put 6 kilo ohms, you're going to have 5 milliamps, all right? And I mean, obviously, the same current flows through the loop. It's going this way, that way, that way, that way, that way, and then to ground. It's the same current, right? The same current, okay? The energy in the 30 microfarad capacitor is just this half times the capacitance times the voltage squared, right? And this is this guy, half times the 20 microfarad times 45, because this V2 is 45 and this is 0, right? So we have 20.25 millijoules. I want to simulate the last example that we've just solved, example 5, using a CAD tool, using LT Spice. Let's take a look at it. This is example 5, drawn using LT Spice. This is V1, this is V2, this is V3. Once we click on this node, we have 50. This node, we have 45. And this node, we have 30.